Welcome, ladies and gentlemen. We're currently working very much in the area of machine learning, and we would like to share some potential with you that we have identified and the potential implementation on serial production implementation. Now, here you can see our agenda. What is our motivation? Why are we working on this topic? Why do we think it's getting more and more important? And we've got an example. We did a POC for clutch temperature prediction. After that, we'd like to give you some details on the tool chain that we're using for training the neural networks. After that, chapter 4, we're going to talk about how to deploy neural networks on a transmission control unit. And then, of course, we'd like to share some results with you before we summarize the talk and give you an outlook. Now, motivation. Now, why are we dealing with this topic in the first place? Almost 3 years ago, we decided that we have to build up some know-how in this area, also in industrial applications, because we have seen that our customers and also competitors are working on this matter. So we've seen AI labs being established and many projects being launched, and therefore we said we need to develop skills and know-how in this area in order to be able to answer customers' questions if they arise, and also in order to find out where the potential lies and how we can improve our current processes. Now, one big advantage of machine learning is, and that's something we realized, the higher the complexity in the transmission control unit, the bigger the advantage offered by machine learning in terms of rule-based software development, which is the standard approach, because you can much better model new complex structures in a neural network. And of course, the third key reason is that development cycles are getting thus shorter and shorter, which allows you to save money. And that, of course, means development must become more efficient. And this is once again where we have seen that machine learning has got an advantage. Now, one example that we would like to share with you is clutch temperature prediction. Here we ran a proof of concept, and in order to show you this is a really tangible technology, and urgent issues in production can also be remedied with the help of machine learning on the transmission control unit. Now, the problem that we're dealing with has been along for quite a while. Now, here we've got the typical clutch package that we use for load shifting. We've got the clutch package, and when the clutch is engaged, then the stamp compresses the package, and the speed difference between the gray and the blue part is reduced. Now, in that process, heat is generated, and that heat, that temperature, well, that should be predicted as accurately as possible, because especially in industrial applications with a lot of high load shifting events, it is very important for our clutch protection functions to exactly know how high the temperature levels will be in order to achieve a long service life at the end of the day. Now, traditionally, we have here used a rule-based simulation model. So that's what was being done in the last couple of years and decades. Software engineers modeled the physical clutch model, which means each part has got a heat transition coefficients. So we set up a physical model of the clutch, and then on the test bench, we adapt it to reality with the help of certain parameters. So that's a high initial effort that also requires a lot of energy and a lot of measurements. And you cannot easily transfer your findings from clutch A to clutch B. So there's always a high repeat effort required for validation on new clutches. On the other hand, you've got only few measurements, and then you try to adapt your simulation model to these measurements. But out in the field, you never know whether it's going to work properly or not, and how accurate your predictions are. And now the second model we now propose is to predict temperature with the help of a neural network. It works more or less in the same manner. Or actually, the starting point is the same, but we then take a different approach. We need a large volume of data. We take a special neural network, which we then train and teach. And all of the expertise that was required to describe the clutch package is no longer required, because that's what the neural network does. We teach the network to learn automatically what the physical interactions in such a clutch package are. And this means that we can teach and train these models much more efficiently, which then cover much wider load case ranges. And the second advantage is once we have developed a good neural network, then we can train it for different clutch types without any major efforts. The only thing that we need for that purpose are the measurements. So the basic prerequisite for machine learning is always data. Now, data is being called the new petrol, so it's highly valuable, and therefore it is very important to gather data in the field in a systematic manner in order to be able to put them to proper use later on. And what is most important is that we need labeled data. Labeled data means that the data also have to contain our results. Now we've got a transmission which comes with thermocouples, and sometimes they might already be on their way to customers, and these transmissions, they collect the clutch temperature data for us. And in addition, we've got the input signals, that is the features, and during the measurements we continuously measure all of the input data, which we then use to predict or calculate the target parameter, namely temperature. So that's what's happening during test drives, and then we receive the respective data that have been collected. Now, if you compare this to other industries, for example, autonomous driving, then we've got a huge advantage, because if you rely on image data, then you've got to manually mark those areas in the image which you consider relevant. But for us, this has already been achieved by definition of the individual features. And well, in just a few cases do we have to cut out the relevant areas, but that's a relatively minor effort. Now let's take a closer look at the concept, and this is where the biggest know-how of machine learning is generated and applied, because training such a neural network is not really difficult, but training the right neural network in the right way with the right data, that's fairly difficult. And the slide gives you just a bit of an indication what you need to do. We've got normal fully connected networks, so these are the standard networks that we use. They are fairly small because we run the computations on an 18 megahertz control unit, and we've got to present data to this neural network in a certain manner. So on the one hand, we've got feature engineering. So we do have some knowledge about physical interactions, and we create certain signals or features, but we've got a time continuous problem. So we have to have full knowledge of the past in order to be able to predict data, in this case temperature. And here we've got such a prediction, and if we start at this point, and if the temperature of the clutch is already at 90 degrees C, then it will heat up much stronger than if we were coming from a lower starting point. So we've got to tell the neural network what the current state is and what the most recent temperature development in a clutch has been, and thus we can come up with a prediction about the expected clutch temperature, which we can then generate as an output. And with that, I hand over to my colleague. Thanks, Markus. Well, one more thing. The time is not running, as I can see. I hope you will stop me if we're getting too long. Now, in the next couple of minutes, I'd like to show you how we implemented all of this, and for that purpose we have deployed a specific tool chain. But there are some basic decisions you have to take first. Now, Markus already touched upon of these issues, because in this physical transmission data, you always have a certain degree of complexity that you've got to render in your neural network. That means the neural network must be large enough in terms of number of neurons to be able to cover these complexities in the first place. On the other hand, due to the TCU, we are somewhat limited, and also limited in terms of its performance. One example to put this into context: we're talking about 80 megahertz ECU with no graphics chip on board. So it's a bit of a challenge implementing this. And on the other hand, as has been mentioned as well, we do have time continuous or time dependent data that we're using. And therefore you need a very specific architecture which is different from the way that you apply if you process image data. And now through iterative loops you try to generate the optimum conditions, and from that you can derive your network architecture and your network size. Now this is another overview of our overall tool chain. Basically, the tool chain contains of code, and that includes our vehicle database here in the upper left-hand corner, where measured transmission parameters, which we obtained through simulation or testing, and now we can use and process these data for the training concept that Markus just explained to you. And then these data are presented to the network during training in a manner that enables the network to learn further. And then here to the right, lower right-hand corner, you can see an excerpt of an output. In this case, you can see the temperature curve for a clutch A temperature. And now here you can see the comparison between the measured temperature and the predicted temperature. And of course, in the ideal case, this here is a data set which the network hadn't seen before. And thus, you can also use this for validation in order to be able to tell, is the quality of my result sufficient or not? If that's not the case, and this always depends on the transmission functions that you want to implement. For example, do you need the exact temperature to the last digit, or do you just want to be able to cover certain temperature peaks? And depending on that, you then have to go through another iterative loop, either coming up with a new training concept or change the network size or network architecture, or improve your feature engineering. And then you go through loop after loop until you have identified an adequate network which you can deploy in your vehicle on the TCU. And then you can once again do further vehicle measurements. But working in a hardware-related environment is not really easy, because, as I told you before, we are mainly working in a Python environment, and here you've got certain libraries and computing processes available which you wouldn't have on a typical TCU. And for that reason, we developed a C++ code for our own purposes, which allows us to implement different network architectures and models. This is a modular code, which basically just means that on the one hand, we can ask a typical function developer to use the tool without any machine learning knowledge. And on the other hand, we can also quickly implement an update process. So if new training data is available, if you want to try out a new training concept, then you can simply replace it in an easy manner, like plug and play. And secondly, at an early time, thanks to our experience gathered up to that point, we can already predict how strongly the neural network impacts our TCU. And here we, of course, calculate the CPU utilization, but also storage coverage. And here, for example, in a 100 millisecond task, we found about 1% of additional CPU runtime in a 100 milliseconds task. And that's fairly good. And in order to be able to cover and model the entire network architecture, we need a fairly high volume of ROM storage space, namely 16%, as you can see here. And now here, finally, once again, another overview to the left. Basically, here we once again, and there are no units on the scales because that's not that relevant. The point rather is to be able to prove that with the help of our neural network we reach a certain quality of the prediction, and if you have a certain shifting operation, or if you engage the clutch where the thermal load is created, and you're heating up or heating down phase, and then you've got engine oil, and you can see that with the help of a neural network we are able to predict the temperature curve fairly accurately, although we didn't go to any further model forming efforts. But then you can see that there are certain areas where we do not have that good correlation, and that's due to the fact that either the neural network has not been large enough to be able to learn these events as well, or maybe the training data that were available were not sufficient to cover all of the operating areas which may occur in such a real-life test. And over here you've got an excerpt from a vehicle measurement, and then here in the blue curve we've got the output generated by our neural network for the clutch temperature, yellow and green, engine speed and engine torque, and down here in blue and in orange the clutch pressure of the clutches being engaged and disengaged. And this is not about a qualitative assessment. We just wanted to show you that at any time of the execution of the transmission function, we are able to output a clutch temperature in real time as the basis for further functions to be executed. And this already takes me to the end of our talk. Let me briefly summarize. We have created a tool chain which allows us to run an iterative optimization process, and this allows us to create neural networks for any kind of problems. I mean, clutch temperature is just one example, and which we can model in the neural network and then deploy them on a standard control unit that we are using today. And that marks the end of our talk. Thank you very much for listening, and we'd now be happy about any questions you might want to ask. Thank you very much.